Recording is rolling. It's Wednesday, October 6th. We're continuing the story that involves universal gravitation and centrifugal motion. We're putting those together, starting to talk about orbits. Let's go back a few hundred years ago to, well, when astronomers were thinking differently about the model of the solar system. Like, what is the model of the solar system? So, what people thought for thousands of years, go back to the beginning of this animation, was that this was going on. This is this dot in the middle that represents Earth. That's a symbol for Earth, by the way. And then everything else was revolving around the Earth. That seems to be what's going on, including this bright spot. That's the sun. You guys see that bright spot? Okay. So from our point of view, that is maybe the most immediate thing to think. You guys know that the moon actually is revolving around the sun. But if you didn't know otherwise, say it's like 1,000 years ago, you didn't know any different, then well, it kind of seems like everything's revolving around the Earth. Now, you guys in this class nowadays know that velocities are relative, so the fact that the Earth is speeding around the sun is not something that you can feel. But you guys understand that. But people did not for a long time because physics hadn't come around. People didn't understand Newton's laws and that sort of thing. Okay. Now, if you pay real close attention to the paths of the planets using this model, well, you already see a problem with this model, which is like these loop-de-loop motions in the sky. The word planet is a Greek word that literally means wanderer, because the planets would wander across the sky differently than the rest of the stars did. All the stars kind of move together, but then these planets would, well, they move across the sky, but they'd have sort of an independent motion. In fact, sometimes they would actually move a little bit backwards in the sky. They would have this retrograde movement. And there was no real good explanation for why that would be the case. It was just observed to be the case. So it's like, oh, well, Earth must be in the middle. These planets must be spiraling around something. And I guess we're going to run with that. Then along comes this guy named Copernicus. He says, well, hold on a minute. I've got a much more straightforward model that makes more sense. I'm going to put the Earth at the center. Or sorry, the sun at the center. What you guys saw before was the Earth at the center. That was called a geocentric model. Geocentric meaning Earth-centered. Copernicus comes along and says, no. I'm going to create a heliocentric model, meaning sun-centered. That's heliocentric, sun-centered. And now the motions of the planets are much more straightforward. Everything's just revolving around the sun. So a whole interesting history behind this too, which is, and this was in a time period where it was against the law to think things like this, in the old European theocracy. So Copernicus actually did not even publish this book until like the day that he died. Like on his deathbed, he got the first publication, and then he died that day. So this was when heliocentrism was first published. This guy named Copernicus. Now, after Copernicus, but before Isaac Newton, which is pretty amazing, comes along this guy named Kepler, and Kepler, Johannes Kepler, was looking at the motions of these planets, very precise measurements of these planets, and realized that actually these orbits were not exactly circular. And he was trying to pin down, okay, well, these orbits are not circular. Exactly what are they? I'm going to play a short Carl Sagan clip for you guys.
Tycho had told Kepler that the apparent motion of Mars was the most difficult to reconcile with a circular orbit.
Yeah, so there's the motion of Mars from our point of view. Looks like it's moving forward, and it has this retrograde movement. Well, what the heck is that about? Well, you guys know from the 21st century that, okay, well, this is all has to do with like relative motion of these planets as they're going around the sun. Oh, yeah, Chris?
Wasn't Kepler and Copernicus Enlightenment, like they were during the Enlightenment era, and they during this time they brought forth knowledge that was like accepted, because typically in the past, if you brought information like this, you'd be like sentenced to that.
Yeah, you're right. Yeah, you're right. So yeah, Copernicus was in danger, so that's why he didn't publish anything until like literally the day he died. And Kepler came after him. So you're right. So these ideas were more in circulation, a bit more accepted. I mean, this was around the time period that I had to be careful. Like Galileo was actually under house arrest for the last few years of his life because he espoused this heliocentric model. But yeah, so Kepler's looking at actually a bunch of planetary data collected by a guy named Tycho Brahe, and well, here, continue the story. I'll fill in some details.
After years of calculation, he believed that he had found the correct values for a Martian circular orbit, which matched 10 of Tycho Brahe's observations within 2 minutes of arc. Now, there are 60 minutes of arc in an angular degree, and of course, 90 degrees from horizon to zenith. So a few minutes of arc is a very small quantity to measure, especially without a telescope. But Kepler's ecstasy of discovery soon crumbled into gloom, because 2 further observations by Tycho were inconsistent with his orbit by as much as 8 minutes of arc. Kepler wrote, "If I had believed that we could ignore these 8 minutes, I would have patched up my hypothesis accordingly. But since it was not permissible to ignore them, those 8 minutes pointed the road to a complete reformation of astronomy." The difference between a circular orbit and the true orbit of Mars could be distinguished only by precise measurement and by a courageous acceptance of the facts. Kepler was profoundly annoyed at having to abandon a circular orbit. It shook his faith in God as the maker of a perfect celestial geometry. Having cleaned the stable of astronomy of circles and spirals, he said, he was left with only a single cartful of dung. He tried various oval-like curves, calculated away, made some arithmetical mistakes, which caused him, in fact, to reject the correct answer. And months later, in some desperation, tried the formula for the first time for an ellipse. The ellipse matched the observations of Tycho beautifully. In such an orbit, the sun is not at the center, but is offset. It's at one focus of the ellipse. When a given planet is at the far point in its orbit from the sun, it goes more slowly. As it approaches the near point, it speeds up. Such motion is why we describe the planets as forever falling towards the sun, but never reaching it. Kepler's first law of planetary motion is simply this: a planet moves in an ellipse with the sun at one focus. As the planet moves along its orbit, it sweeps out, in a given period of time, an imaginary wedge-shaped area. When the planet is far from the sun, the area is long and thin. When the planet is close to the sun, the area is short and squat. Although the shapes of these wedges are different, Kepler found that their areas are exactly the same. This provided a precise mathematical description of how a planet changes its speed in relation to its distance from the sun. Now, for the first time, astronomers could predict exactly where a planet would be, in accordance with a simple and invariable law.
All right, so that's the first 2 laws of planetary motion.